Okay, and to control it, you can control it here. Okay, so perfect. Got it. Okay. I don't need. Do I need an introduction? I need an introduction.
So thanks everyone for coming. It's my great pleasure to introduce today's speaker, Jenny Sprintall from SIO. She's visiting PhD this week as CMS visiting scientist. So many of you have known her for a long time, and most of you have talked with her in the past 2 days. She's very nice, and I had the opportunity to, I was really fortunate and opportunity working with her and Sarah Gailey as a postdoc. I really have learned a lot from them. And so Janet has been involved in many observational programs. Just for one, closely to what we do here. She is PI for SIO SBT program, and she's also working with Gustavo together as co-chair for SBT science working team. So she has worked a lot in the Southern Ocean, particularly Atlantic Passage area, which she will talk about today. And she also, another area she worked about is Indonesia through flow, and she will talk about tomorrow cross strait. So
okay, thank you very much, Jennifer. Thank you. Okay, so this is the talk today is about climate variability in Drake Passage. This is the platform where we take our measurements. A very blurry day in the Drake Passage. It's the Ellen Gould, and I'd like to acknowledge my co-authors for this talk, Colin Sweeney, who's at Ceres in Colorado, Terry Tereskin, Sarah Gilly, and Chuan-Li Jiang. Okay, so a brief outline. I'm going to start off with some motivation and background. Well, how do we expect the Southern Ocean to change in a warming world? Then I'm going to move to the underway measurements from the Drake Passage itself in this region, which the Drake Passage is actually the cold route on the thermohaline circulation. And tomorrow I'm going to move and talk about the warm route, but today let's stay in the Southern Ocean. I'm going to move to signals, long-term trends, and maybe even longer long-term trends. Some work that we did with Chuan-Li about what we can learn about carbon changes in response to a changing Southern Ocean. Okay, a bit of background first. This is everybody's favourite Southern Ocean circulation slide. This one is adapted from the NRC report in 2011. And here we see the Antarctic circumpolar current, and it's characterised as a region of heat gain. It's driven by these strong westerly winds. It's heat gain as well as carbon uptake and a biological and solubility pump. And what I'm going to focus on today primarily is on the shallow MOC circulation. So this is the upwelling of circumpolar deep waters into the Southern Ocean that then move northward through the Ekman layer and get subducted at the deep mixed layers to the north of the polar front and the north of the subantarctic front, actually, as intermediate waters and subantarctic waters. And obviously the rate of transformation of these water masses, these two global water masses are found in the global ocean, also heat and carbon within the global ocean. Do you think I'm doing something to this? I think I'm moving something there.
You just minimize it and then click
push the green button, right? That one? Not the red one. Not the red one.
Right. No, that's right.
You want me to take the red one? No, this one. This one. Perfect.
And then click on the screen to make your PowerPoint.
Click on the screen?
Yeah, click on that.
This like that. Okay, so still in the background. What we have at the moment in the Southern Ocean has, much of this is going to be familiar to many of you, but I like to just put forward a bit of a primer about what's going on in case there are people in the ocean, in the audience whose focus is not the Southern Ocean. So the Southern Ocean has been experiencing much stronger westerlies that drive this Antarctic circumpolar current, and that has been driven, it causes ACC to shift poleward because of the stronger westerlies, and that's mainly a manifestation of the southern annular mode. This is the geopotential height pattern associated with that mode, and here is the time series. At this stage, taken from the IPCC report in 2007, so it only goes up to 2007. So we'll see it's mainly been in a positive mode since the 1990s, but there's been some variation on that on interannual timescales, and I'll talk about that later on in the talk. So what does SAM mean for how it impacts the Southern Ocean dynamics? Well, there's two hypotheses, two trains of thought, and the first one is that changes in SAM drive these changes in the axis of the ACC, they drive changes in the front, and they also drive changes in the transport. So how this comes about is that these increased winds lead to this increased northward Ekman transport, and then that enhances this downwelling of the intermediate and mode waters to the north and causes then the upwelling of deep carbon-rich waters to the south of the ACC. And the overall impact is that we expected to have an increase in the shallow MOC circulation as well as an increase in the isophysical tilt of the ACC. This is shown in some work that we did with Shenfu when she was a postdoc with Sarah Gilly and I, and this is, she showed that the meridional displacement of the band of the maximal wind stress, that is the westerlies associated with the ACC, lead to and are coherent with the meridional displacement of the time series of the polar front. The second hypothesis is that changes in SAM drive changes in the ACC eddy transport. So in this case, the increases in winds lead to a much stronger eddy field that's then effective in dampening the zonal momentum of the ACC. And the main support for this comes from eddy resolving models as well as altimetric measurements of EKE, such as shown here by Meredith and Hogg. And finally, SAM also impacts the Southern Ocean mixed layer depth. This is shown by work by J.V. Soleil a couple of years ago, and we actually get, what is noticeable then is we get non-homogeneous or inhomogeneous changes in the mixed layer depth at different places around the Southern Ocean. And of course those changes, those non-homogeneous changes in mixed layer depth then also impact the way the Southern Ocean takes up carbon and other properties of biological productivity. Of course, the Southern Ocean accounts for about 40% of the global oceanic uptake of carbon. So these changes are vital for our understanding of the carbon cycle. And what we see here is that there's actually been a change in the rate, there's been a change in the rate of uptake of carbon in the Southern Ocean for working Takahashi. And this has shown that the uptake of surface water carbon at SST is significantly increased, especially when we correct for SST, and that's occurring at a faster rate than the atmospheric uptake. And so this implies that there is a weakening in the oceanic uptake of carbon. And let's not forget ENSO variability in the Southern Ocean. SAM and ENSO indices are often anti-correlated, and this is a very complex interaction then between these two large-scale climate modes, right? Some effort has been to separate that, and again, this is work from J.B. Soleil, and it shows here, this is the correlation, the covariance of the polar front location with SAM in black and with the ENSO indice in grey, and you can see, and around the Southern Ocean, this is longitude on the x-axis. So we can see there's great spatial variability in the response, and in fact, if we separate out the high frequency response, that is less than 3 months, we see a stronger correlation to SAM events, whereas at the low frequency, for longer timescales of greater than a year, it seems to have a greater coherence with ENSO variability. And last but not least, there's also been changes in Antarctic sea ice coverage, and that's shown in this recent paper from King that shows that there's not only that there's an inhomogeneous spatial response in sea ice variability. So here in this region where I'm going to focus, along the West Antarctic Peninsula, has been a region of strong sea ice loss. This is a trend over the last 20 years, I think. And then, whereas other regions, like the Ross Sea, have been regions of strong sea ice gain. Okay, so that's my background. And so I'm going to discuss different aspects of this climate variability using our Drake Passage underway data system, right? This is, has a WOS designation of AX22. It started actually up on the Polar Duke, and then we shifted to the Gould when that came online, I think, in about 98. So it began with the high resolution XBT program in 1996, so that's 18-year time series we're talking about. The Gould actually traverses the Drake Passage 20 times a year, so that's 40 transects. It's pretty amazing. It's going from Punta Arenas in Chile down to the Antarctic base, the US Antarctic base, Palmer Station, down here about 65 south. Transporting supplies to Palmer Station, as well as scientists who do research along the Antarctic Peninsula. So in 1996, we started this XBT program. The XB is part of the high resolution network that AOML is also heavily involved with, and we at Scripps are also a big component of that. We have very close spacing of 6 to 12 kilometres across the Drake Passage, because we have this, the ACC is characterised by these strong fronts, so we really need to resolve those, and they can shift very rapidly, and the changes in temperature occur over very short space scales. We take about 6 to 8 transects per year, and so we've got 112 temperature transects today. So what is unique about this is that it is year-round, okay? So we're getting summer, winter, all year-round measurements of the Southern Ocean. In 2001, we supplemented the XBT measurements with XCTD sampling, and these are much more expensive, an order of magnitude more expensive than an XBT, so we've got to be careful. It's like throwing over a television set every 50 kilometres, so we only drop about 12 of these. You know, there's 25 to 50 kilometre spacing of these. And then in 1999, Terry Tereskin, at that stage also with Eric Fearing at the University of Hawaii, introduced, drilled a hole in the hull of the Gould and put in a ADCT. At that stage, it was a narrowband 150 kilohertz, and so she has 296 transects of ADCT velocity. And then in 2004, they also put another hole in the hull with an Ocean Surveyor 38 kilohertz, and she has 169 transects of these much deeper. The 38 kilohertz extends down to 1,000 metres, roughly 1,000 metres deep. In 2002, Cole Sweeney introduced the PCO2, underway PCO2 sampling, and you can see here is this figure is from Takahashi, or maybe Rick Wanicoff's updated version, and it's showing the number of months of at least one PCO2 measurement available since the 1970s. So you can see the Southern Ocean is really dominated. For what we understand about carbon cycles in the Southern Ocean really strongly is influenced by what we understand about carbon cycles in Drake Passage, observed, in the observed system. And then just really recently, Britt Stevens, who's also in Colorado, introduced atmospheric O2 and CO2 measurements. And the Gould also has a MET system and a TSG system, and all of this data into the SAMOS database. So how am I doing? Okay, so there's been many studies. We've had about 30 papers related to variability of observed variability in the Drake Passage. as well as 4 PhD theses at Scripps with using this data set. So this combined underway measurement system, we've been able to look at eddy heat and momentum fluxes because we have coincident measurements of temperature and velocity, mixed layer variability in the Southern Ocean, as well as lots of validation of satellite measurements, of remotely sensed measurements that Shenzhou is responsible for. And then more recently we've started looking at seasonal drivers of carbon in the Southern Ocean. These seasonal cycles were very much unknown before we had these. We had these measurements in the Drake Passage. So let's start with just some basics. This is the mean temperature section in the Drake Passage. The white lines indicate the variability in degrees C. And we can see that this is the mean location of the polar front. It's defined as the northern extent of the 2 degrees C isotherm at 200 metres depth. And so you can see that polar front clearly separates 2 water masses. This is the sub-Antarctic, warmer sub-Antarctic water masses from the Antarctic, the much colder Antarctic water masses. In the lower panels, we have the seasonal patterns associated with that. And we see summer is characterised by a winter water layer. That's a very cold sub-zero water mass, capped in the surface layer by a much warmer, seasonally varying surface layer, but in this case in summer it's much warmer. And there's obviously a salinity signal to go with this to make it stable, but in the winter water, and that starts to get eroded in fall, and by winter it extends up all the way up to the surface layer. So the upper 150 metres is characterised by what we now refer to as Antarctic surface water, and that is this sub-zero water mass here that extends all the way to the polar front. And you can see how the polar front is much sharper during winter, and so much so that it's resolved. That's why we have these very high resolution measurements, because it is really resolved by 3 or 4 XBT profiles. So within about 30 kilometres, it's a very sharp front. So we need that high resolution measurement. Okay. So the cold front is also, as you'd expect, associated with a strong velocity jet. This is shown in this figure from Yung Ling's thesis, and all these dots correspond to the location of the polar front as defined by temperature, as defined by the XBT temperature. And you can see in each case it's associated with a strong velocity jet, although you can see other, as well as the sub-Antarctic front is also equally characterised by a strong velocity jet. But you can also see evidence in some transects, in some, this is the ADCP velocity at 150 metres, and you can see lots of evidence of eddies and lots of variability across the front and between the fronts as well, although we tend to see these bands of strong velocity associated with the front. Whereas at the southern ACC front, which I won't talk about much in this talk, but you can see that it's not, we think it's not very well resolved by temperature. It's well resolved by velocity. You can see a weak velocity jet at the southern location of the of Drake Passage, but it's not very well resolved by temperature. And finally, I'm warming up to why the Drake Passage is a very good region to look at changes in the polar front, right? And so we see that it's associated with this strong jet. We also see that it is a singular jet, a singular front in Drake Passage. And I can show you a number of different figures to illustrate that. One from Sokolov and Rintal, who looked at frontal variability resolved from altimeter measurements. And here also is another example from Shenzhou's work, and she looked at she resolved the front from SST measurements, from microwave SST measurements. And so you can see and the mean location of the front is shown by the black line, and the grey shading indicates that variability. So you can see that in Drake Passage, there's very little variability, very little movement in the front. And again, here is this is work by Yung Len that shows that the PDF of the polar front in terms of the streamlines from the XBT measurements as well as with the dynamic, matched against the dynamic height measurement, shows a very narrow range of probability that the polar front will fall within a 5 centimetre dynamic height bin. So there's really just this one, whereas in other regions of the Southern Ocean, we might have a southern polar front, a northern polar front, you know, a southern subtropical front. This in Drake Passage is just this, the multiple fronts that might exist out here in this very quiescent region of the South Pacific coalesce into one front as they move through Drake Passage. So in terms of seasonal cycles, there is a very tiny seasonal cycle of the polar front and the subantarctic front in Drake Passage. It explains only about 5 to 10% of the variance. So you can see a slight shift. You can see a slight shift. It's further, the polar front is further south at the end of summer, and then shifts towards north in the austral winter. No, that's austral summer. Sorry, I'm getting confused. But the explanation is the variance explained by the seasonal cycle is very small. So then, if we look for shift, the trend in the Drake Passage. Now, recall we have this increased sand variability, and one of the hypotheses is that should lead to shifts in the polar front. And so what we've got here is the sand index over the record length of our XBT time series from 96 through till mid-2014. And so you can see it is mostly positive, but then it's characterised, like I said, of, you know, strong periods of positive variability, followed by, since about 2011, of very weak positively. You know, it's just hovering around zero. It's positive in the mean, but it's just much weaker over these past 3 years. So as I mentioned, there is this work from Sokolov and Rintoul, who shows that there's this global average latitude shift of about 35 to 40 kilometres occurring over the decade in the Southern Ocean fronts, and this is resolved. But this is resolved from sea surface height variability, right? And so there's the spatial resolution of sea surface height is, you know, much coarser than what we can have in our XBT measurements. So in fact, if we look at the trend of the polar front, I did this a few years ago. I started looking at this a few years ago. And so up till about 2011, when we had quite a strong phase of the southern annular mode, then we found, oh, I forgot to tell you, I'm sorry, in our XBT transect, we have 120 transects, right? But many of them lie in the middle transect. So 70 of those transects go straight down from Isla de los Estados, from the Tierra del Fuego, exactly, to, they follow the 65 degree west meridian, right? Okay, so just to, in case you're thinking, well, you know, you've got a big wide band of XBT transects, and so it could be zonal changes in the front. But if I look at the trend of the polar front, just from those middle transects, I get a shift, a southward shift over the time series through 2011 of about 50 kilometres, whereas if I consider the whole lot, then I get about 58 kilometres. And these are significant trends southward of about the same magnitude as predicted by the model. But as I keep increasing that, the trend is decreasing now to 47 kilometres, and then up until the end of 2013, it's about 38 kilometres. It's still significant, but then once I've included this last year, the middle transect is no longer significant, just no longer significant, but if I include all transects, then it's still significant, but only barely. So it's still, I mean, we're seeing a response. We are definitely seeing a response of the polar front shifting to the wind shifting, as we'd expect, but it's not as clear-cut as what as it has been in the past. Okay, so I'm going to move now. Okay, we're doing good. I'm going to move now to trends, right? So we're going to look at water property trends, because we'd expect with this shift in the polar front that we might get changes in the temperature and salinity characteristics of the Drake Passage. So I just wanted to spend a moment explaining how we get salinity, right? Because although we resolve temperature really well, right? This is the section in March of 2014. So you can see each of these dots along the top axis shows a location of an XBT profile. So you can see we resolve that winter layer. If I showed you the altimeter measurements that go with this and the ADCP velocity measurements that go with this, you could see this is likely a eddy just north of the polar front here, and then this is the subantarctic mode water. The subantarctic water. Actually, this is the subantarctic mode water right here. But you can see a lot of variability. Whereas, as I mentioned, our salinity, like in this case, these are the locations where we dropped XCTDs along this x-axis, and so there's only 12 XCTDs. But if you look at the salinity signal associated with those XCTDs, you see that we get a corresponding signal in salinity associated with those eddies, with that eddy variability. Whereas if I just use the salinity climatology, as we often do with XBTs, matched to the XBT temperature. So it's like a GEM lookup table, right? So we have temperatures with depth, and we have a salinity from the climatology. I don't see even a hint of this thing. So we want to correct our XBT salinity, our TS climatology for this observed variability. And so what I do then is I map the salinity anomalies of these two, of the difference between these two salinity fields, and onto this climatology and correct it, right? And so now we have the corrected salinity that clearly shows the evidence of that eddy, for example, and much more variability in the salinity field, a more realistic salinity field than what we get just from climatology. So when I talk about trends in salinity, it's using this corrected salinity field. Okay. In terms of, I just wanted to orientate you, because I'm going to talk about property changes on depth surfaces, which is shown in these upper panels, temperature on the left, salinity on the right, and in the white contour line will delineate the 0 degree C isotherm as well as the 2 degree C isotherm. So we can see that in both the temperature and salinity fields. And I'm also going to talk about these changes on neutral density surfaces. And again, I have delineated the 0 degree C isotherm. And can you see the 2 degree C isotherm? Maybe. Maybe I'll point it out anyway, just to orientate you, because that 2 degree C isotherm actually characterises this upper circumpolar deep water, right, which is the most voluminous water mass that we have in the Drake Passage, and probably actually in the Southern Ocean. But there's very little variability in the shallow. It shows extremely little variability, roughly around 2 degrees, and so in density space, it only occupies a small region. Okay, so if we now look at, these are the water mass trends in Drake Passage. They've all been de-seasoned, de-mean. So this is over that 18-year time period. We're moving from north to south. This is the location of the polar front here. So actually it's showing the shift from south to north. And these are changes now on isobaric surfaces due to adiabatic movements of water mass, in relationship to wind changes. So these are showing a slight cooling at the south of the mean location of the polar front, but north of the polar front is really characterised by a full depth warming, much stronger in the surface layer. Again, these have been de-seasoned and de-meaned, but the variability in the surface layer is going to be influenced much more strongly by the seasons. Below 100 metres, it's not much seasonal variability in the Drake Passage. And then in salinity, here I've used the corrected salinity from the Southern Ocean database, but if I showed you it in relation to the World Ocean Atlas, it's pretty similar. And so we see in that case it's characterised by a strong freshening in the region just south of the polar front, just south of that 2 degrees C isotherm, and that's as well as at depth, the depth north of the polar front. And this region is fairly significant because it forms the source waters for the Antarctic intermediate water. These are the source waters that are going to be blown north in the Ekman layer to form the Antarctic intermediate water in the southern annular mode. The subantarctic mode water. If we look at those trends now on density surface, we see that we actually correspond to a freshening and a cooling now for neutral density surfaces less than about 27.3. Here's that white line shows the 100 metre is corresponding to the mean 100 metre depth surface. So we can see that extends, this cooling and freshening mainly occurs above 150 metres, whereas the upper circumpolar deep water is shown as being as warming and salinifying. And so these are sometimes confusing for people to try and work out why it's very different on neutral density surfaces versus the isobaric changes. And actually we can resolve that by looking at something that you probably can't see because I can't. In green, okay, so let's have a look at the blue line is the mean temperature and salinity curve for the 10-year period from 96 through 2005, whereas the red line is the mean TS curve from 2006 through, so the last period, right? And so, and the green arrows connect these mean TS at certain depths, going from the surface down to 800 metres. And so if we look in the surface layer, we can see that at 100 metres, right, which is characterised in 96 by this dot, is warm and fresh on the 100 metre surface, right, because we're moving from this dot to this dot, so it's warming and freshening, whereas we look on isopycnals, it's actually cooling and freshening. And similarly, when we get deeper in water columns, instead of it appearing to be warm and fresh, for instance, on this 550 metre pressure surface, it is actually warming and salinifying on the isopycnal. In terms of density changes, if we look at it, there's a number of ways to look at this, but I'll just show it in terms of depth. These are the mean temperature changes with depth, mean salinity changes with depth, and these are the mean density changes with depth. So we see near the surface, it's primarily salinity-driven changes, whereas at depth, it's primarily temperature-driven. Whereas we look across the passage from north to south, these are the temperature changes, salinity changes, and density changes. We see both properties contribute to these density changes. But in terms of whether this is, you recall I said there were two hypotheses, whether this was due to shifting in the, an increase in the eddy variability, in which case we'd expect to be no tilt in the isopycnal. Indeed, over these 18-year changes, this is the density gradient change from, in red in 1996 to 2014 in black, and we see only a very small increase in the isopycnal tilt here, shown between 200 and 700 metres, and in fact a small decrease in the tilt. And so this in the end actually implies very little in the ACC transport, which is supporting previous measurements that, of bonings and all, and who looked at global Southern Ocean mean things. So what's causing these changes? This is very much work in progress, so we're still investigating this, but of course it could be related to increased precipitation in the Southern Ocean or in the global ocean. There's this increase in ice melt, sea ice melt occurring around the Antarctic Peninsula. It could be these increased winds do drive stronger northward transport, or it could be the frontal shifts of the fresher, warmer waters from the north. But either way, they have implications for the intermediate water and mode water formation properties in Drake Passage. Okay, so I think I'm going to I will have time to talk about, I'm going to shift gears a little bit, and I'm going to talk about this second project that we've all been involved with. Again, this is work in progress, this project is looking at the variability in the Drake Passage properties, but just in respect to climate modes. See if we can tease out what these changes are, whether they're due to changes in the SAM index or changes not changes in the index, changes in SAM versus changes in ENSO. But we will use the indices to form composites of the polar front and the Antarctic surface water properties based on strong positive or negative values. So we're going to form composites according to what phase of SAM or what phase of ENSO we're on. And so we're going to focus primarily here south of the polar front, as I said, in this upper layer, in the winter water and Antarctic surface water, and that's also beneath, so that's shown here in this temperature section, and also this PCO2 section that Colm Sweeney undertook here in March of April of 2006, and that's showing that this voluminous upper circumpolar deep water is extremely rich in PCO2. So if there were changes here from upwelling or something like that, we'd expect to see changes in PCO2, in the measured PCO2 of that water mass. So I'm going to focus then on this region. I'm going to look at variability in the polar front latitude, in the Antarctic surface water, in the inventory, the amount, the volume of area of Antarctic surface water, the temperature of that water mass, the depth of that water mass, and also then changes in the PCO2. And if we do that, that's what we get. So on the left-hand side, these are composites of positive SAM events for wind changes, for the polar front location, for the temperature of the Antarctic surface water, the area of Antarctic surface water, the mixed layer depth, and the del PCO2 of that Antarctic surface water. On the left-hand side is the positive SAM events, and on the right-hand side is La Nina events. I could show you, negative SAM and El Nino events, but they're just really the inverse of this. So I'm just going to show you this. So we see both positive SAM and La Nina are characterised by enhanced westerlies. They're both characterised by a poleward shift of the polar front location, and they're both characterised by slightly warmer water. But then we see it's only during La Nina events where we get a decreased inventory of the Antarctic surface water, a shoaling of the mixed layer depth, and a decrease in the del PCO2. That is, the ocean is a net source of carbon from the air. Now, why? Yes, so only that's just enhancing that. So here in the left-hand side is just a repeat of what I showed, And here on the right-hand side now is just looking at what might be forcing that variability. It's very new work, but we've just started to look at, and we should look at the spatial patterns, right? So we haven't looked at the spatial patterns associated with this. This is just the change in the meridional wind stress during SAM and La Nina, and also a change in the total heat flux, right, associated with La Nina and SAM. And we see they're both characterised by stronger southward flow of this warmer water from the north, as well as an increase in the heat flux into the water. And if we look back at the envelope sort of calculation, it can account for these sorts of anomalies of about 0.1 degrees C. Whereas if we look at the what might be causing the differences, what might be causing this change in the area, this decrease in the area, this decrease in the mixed layer depth, as well as an uptake of del PCO2, a change in the del PCO2 ratio, we see that upwelling is occurring. There's an increase in upwelling occurring in La Nina events, not during SAM. And so our thinking at the moment, although again this is very much work in progress, and we need to, I really think, yeah, we need to look at the spatial patterns rather than just these composites. We can look at the composites, but we need to look at the spatial variability of the composites. So what we think is happening in SAM, we get these stronger westerlies, and there is this poleward shift in the polar front. We get increases in the heat flux, and that leads to a warmer Antarctic surface water. Whereas during La Nina, we also see the stronger westerlies. We get a shift in the polar front, increased heat flux, but we now see an upwelling of warmer PCO2-rich upper circumpolar deep water, and that's in response to mixed layer shoals, and so that's leading to a warm and PCO2-rich Antarctic surface water. Okay. It's from the wind stress. It's from the wind stress. It's curl, the curl.
The outline.
Yeah.
But the wind has changed in both the outline.
Say that again?
If the wind has changed in both situations, the outline.
Yeah, it's got to be this. That's why I need to look at the patterns. I need to look at the patterns because I think that, you know, there must be subtle changes in maybe the meridional winds, right, that occur in different regions downstream of this. I think it's true. I think this is a good point. I think it's a good point. I think I will, in the interest of time, because we because we got started late, I think I will skip this. Should I? I've got 5 minutes.
Keep going, yeah.
Okay. Thank you, Molly. This won't take very long, and maybe there's some people who are interested in this. This is new work by Shuangli Jiang, that when she was a postdoc with Sarah Gilly and I. And this is looking at evaluating the CMIP5 coupled carbon model, coupled carbon climate models, the Earth system models. And what we did was we used the surface water PCO2 and underway measurements to evaluate these Earth system models. So in this case, as you know, the CMIP5 Earth system models couple the ocean carbon cycle with the climate models, whereas in the past, these Earth system models have prescribed the PCO2 concentration scenarios, right? So what I'm going to show here today, actually from 2002 through 2011, it's using the historical measurements, and then from 2006 through 2011, we're going to look at the RCP 8.5 scenario. That is when the radiative forcing reaches this value by 2100. Okay, so here in the top panel is looking at the mean bias, right? So this is the differences between the Earth system models and the shipboard mean PCO2 data. And we see that, so if it's positive, it means that it's more than observed. If it's negative, it's less than observed. And so we see that in the mean that they do quite a good job. It's mostly less than 6 atmospheric microatmospheres. There's a bit slightly bias in summertime measurements. That's the clear bars. And then in terms of seasonal bias, we have in this top panel is the total seasonal PCO2 measurements. The observations are shown by the black line, solid black line in each case. And so we can see this is, in top panel is the total seasonal PCO2, and then we've broken it down to the SST force PCO2 section derived seasonal cycles and the DIC force PCO2. We can see that that's out of phase in this region of the Southern Ocean, those two seasonal cycles, whether it's SST forced or DIC forced, are out of phase. And we can see that the DIC forces are high in winter, and that's because the mixing of this this DIC-rich deeper waters, the upper circumpolar deep waters, and so they're out of phase. But the amplitude, the model amplitude, far exceeds the observed amplitude, and that's because of these model biases in both SST force and DIC force variability of PCO2. So what's wrong? What might be causing this? Well, the first thing we looked at was what are the winds like that are in these Earth system models, and what are the surface currents like. Down here are the observations, and those observations for the winds are CCMP winds, and in the currents are from Oscar, and we can see that in many of these models, especially these highlighted models here, the winds are much too strong east of 65 west, and so that's leading to an increase in the sea-to-air carbon flux, and an increase in this DIC-rich deeper water, and it's also going to drive stronger northward Ekman transport of this DIC-rich water. The surface currents are also too far northward, and that's also going to carry this carbon-rich water to the north and too far north so that it's not subducted as part of the intermediate water. In terms of vertical stratification, this is the observed stratification down here from the World Ocean Atlas, and so it looks very similar to the XBT mean temperatures that I showed you from the past, the patterns in XBT that I showed you in the past. We can see now, in this case, the stratification is way too strong north of the polar front, and that's making the upwelled carbon much harder to subduct, whereas south of the polar front, the upper circumpolar water is much too cool and strongly stratified. So what's the verdict? Within Drake Passage, these models are likely to release too much carbon to the atmosphere, and then that reduces the inventory of carbon, dissolved inorganic carbon in the model Drake Passage. These shipboard measurements that we have, though, provide a very valuable benchmark for assessing these. They provide one of the only time series, year-round time series, to assess the performance of these models. But we don't know whether they're representative of the entire Southern Ocean, because our measurements are clearly biased by, our measurements of the Southern Ocean, of what we understand in the Southern Ocean, are biased by the measurements in Drake Passage. Yeah. Okay, so that's conclude. Thank you, Molly. So that's just a flavour. You can go to the paper. You can go to the paper, or you can talk to Shronley or whatever, and I'll give you a copy of that paper. It's a lot more detailed, but I just wanted to let you know that it's out there. Okay, so the combined Drake Passage underway data set temperature, salinity, currents are the only all-year-round repeat underway measurements in the Southern Ocean. I showed you a couple of preliminary studies. 18-year trends show a poleward shift in the polar front, and there's this freshening in the near surface layer, and that's characterised by warming and solidifying on the isopycnals in the upper circumpolar deep water, and that's consistent with warming and freshening at the base of the surface layer, right? The upwelling of the warm carbon-rich water appears to occur under La Nina conditions, possibly due to changes in the wind curl. And the CMET5 Earth system models need improved wind and stratification fields to model carbon exchange in the Southern Ocean. Thank you. So just a few piecemeal, presentations, and I'm happy to talk about any of this. I'll take questions now, of course, but I'm happy to talk about this with anybody later as well. I'm here until Friday afternoon. We can talk. Yes, Lisa.
So the trend of the total function, and then you talk about how that trend has kind of slowed in recent years.
That's right. That's right.
Do you have any feelings for why?
I think it's been this slowing. Yes, it's a change in the winds. I think that the winds have also slowed in the past. I do not know of anybody who's measured that, but the SAM would indicate that, right? The SAM has changed in the past few years, so it is more. It's still positive, but their strength is not the same. And I don't know. Does anybody know? This is very much work in progress, but I see, changes in the strength of the SAM, which indicates strength of the wind. And so it could also be, I don't know. But it's a good question. Yes.
I don't know why, but it reminds me of Sylvia and Gustavo and I have looked at the latitude of the confluence, the Malvinas confluence.
Yes.
And we noted that that in the late 1990s, it shifted south pretty significantly, and then seems to have been fluctuating around this new position since, through the 2000s.
Right.
Which sort of reminded me of what you showed in the latitude or location of the
exactly.
polar front.
Exactly. I mean, it's very, we're going to get this. Yeah. I mean, these, so you can see that, right? I mean, this is only from 1997, right? So, when it has been, but still, you can see the fluctuations about that.
In the earlier period, yeah, the
yeah.
It seems like quite significant, and then not.
Exactly. And so, like here is wishy-washy, and we're going back into a weaker stage again.
Yeah, I wonder if these are correlated.
It is. I know that this is. They have a long-term LTER time series in Drake Passage, just around Palmer Station and actually on the peninsula, and they see 6-year cycles in their ice records, that they feel is strongly correlated to this. But then other earlier studies had shown that it was very hard to by Kwok and Cosme. I always get his name. Cosima? Is that JPL? Anyhow, he's a nice guy. And a nice guy and a nice guy. He used the satellite measurements to show that changes in ice on the peninsula is hard to discern whether they're ENSO or SAM related. And so his measurements, the measurements they have as part of LTER, are for just a record like this, a 20-year record. And so it could be that it's more dominated by SAM at different times of the year. Yes, Renellis.
So even though the correlations are becoming less significant because the nature of the trend, even though the trend is becoming less significant, the nature might be different. What about the correlations to the SAM? Maybe the significance of that
good point.
Is increasing as you add more.
Good. Yes. Okay. I haven't even done that basic sort of analysis. Yes. That would be good, right? That would be a good thing to follow. Mental note. That's a good suggestion. And also because it's very tricky, because it is, the SAM and ENSO are pardon?
You didn't any change in the stratification there, right? In the stratification of
in the tilt, yes, right.
So
Or very small, very small.
Right.
Yeah.
Do you have any way to measure if the eddy variability?
Is the eddy? Through the satellite measurements, I think we could, like the eddy kinetic energy through the satellite measurements. So I could do that, or you could do that, or I think that would be the way. I mean, we can get that from the locally. We can get it back from the ACP measurements, right? Mm-hmm. And so that would be, and now we have a long enough time series. It started in '99, so we have a 15-year time series. It's not really long, but it starts. You can start to look at trends. You can definitely start to look at trends. So I'll suggest that to one of the students who's working with Terry. This is very good idea. Okay, well, enjoy. Hi, thank you. Yeah.
Say hi, Janet.
How are you doing?
I enjoy your talk, and it's great to see you in Miami.
Yeah, it's good to be here.
Yeah.
It's good to be here.
Yeah, we've